Life is the most complex thing in the known universe. Just ask anybody in the White House. Abundant on Earth, hugely successful in colonizing every available niche, it seems that once started, life is unstoppable. But does that mean there's life on other planets elsewhere in the universe? So far, we have not seen signs of life elsewhere, and not for lack of trying. Is there other life or traces of former life out there? Is there now, or has there ever been, intelligent life anywhere but on our Earth? With 100 billion galaxies, the order of 100 billion galaxies, each containing the order of 100 billion stars, most of which we now know have their own planets, the probability of life having evolved elsewhere seems very, very high. Indeed, on the numbers, it seems highly likely that intelligent life has evolved in the universe at some other time, at some other place, and maybe is out there now. How will we find out for sure? Tonight, we're going to take you on a journey from Earth through the solar system to planets around other stars in the search for life. Let's start with the Earth. And I note that some have asked whether there's intelligent life on Earth. I believe there is. But let me turn it over now to Gavin Schmidt. Gavin?
Earth is the only example we have so far of a planet with a biosphere. As we get further away, Earth shrinks from a recognizably inhabited place to a blue dot, and then to just a tiny point in orbit around the sun. The further out we go, the harder it is to tell that there is life on Earth. But there has been life on Earth for more than 3 billion years. The universe has existed for 13.8 billion years since the Big Bang, and our solar system has been around for the last 4.6 billion years of those. But remarkably quickly, after the solar system formed and rocky planets condensed and cooled, there was liquid water on the surface of our planet. For a planet 4.5 billion years old, we have evidence of water from only 0.2 billion years later. But it took life perhaps another 500 million years to appear. Early life forms weren't much to look at, but life itself has been here a long time. We don't yet know how life got started. There are many theories, but we do know that it got going under some very challenging conditions. The sun was 30% dimmer than today, but with more solar flares. There was no oxygen and therefore no ozone layer to protect the surface from harsh ultraviolet rays. But Earth did have the ingredients necessary to support life: a solvent like water, an energy source, and abundant nutrients. For 1.5 billion years, this primitive life survived in the oceans, protected by the water's opacity. But around 2.5 billion years ago, bacteria started to use sunlight directly to fuse water and carbon dioxide to make sugars, which were then used as food. But for every molecule of carbon dioxide they used, and there is a lot of carbon dioxide in the atmosphere, they released a molecule of oxygen. Those bacteria were followed by photosynthesizing algae, mosses, and plants, and eventually, after a number of false starts, the oxygen built up in the atmosphere until around 500 million years ago, it got close to present-day concentrations, giving a start to the huge variety of land animals, insects, and plants we see today. Meanwhile, the climate was not static. The planet went through cycles of snowballs and hothouses, driven by plate tectonics, volcanism, greenhouse gases, and impacts. Indeed, it was only after the last snowball Earth event that the stage was set for the evolution of multicellular life in the Ediacaran 600 million years ago. The new species that were rapidly born, evolved, and died changed the planet forever. The surface became completely covered, you could say infested, with life. And that life affected the climate, changing the composition of the atmosphere, the reflectivity of the surface, and the cycling of water, radically transforming the view from space. Life co-created the broad array of special, unique ecosystems and microclimates that characterize the Earth today, visible even from 1 million miles away. But remember, for most of the time that life existed on Earth, it did not have a land fingerprint, and the oxygen that we now rely on wasn't detectable for perhaps half that time. Under those conditions, or any others in Earth's history, how can we know what would have been seen from further away? This is where our understanding of current climate and of processes that control composition, clouds, and dynamics come into play. We can simulate the impacts of climate on life and the impacts of life on climate at each stage of our planet's history. Simulations which include the physics of clouds, oceans, ice, and of atmospheric particles like dust. We can take those results and then project how those climates would look from space, from beyond even the solar system. But we can go further. We can even simulate the climates of Venus and Mars 3 billion years ago, when they were both very different places. Places that perhaps also had the seeds of life. And Jen can discuss that.
If life ever existed in our solar system, then it found a way to adapt to extreme conditions. Conditions that may be more extreme than what we have on Earth. I am constantly amazed to find that life has adapted to every niche, no matter how harsh the environment. Take, for example, the extraordinary springs of Dalal in the Danakil Desert of Ethiopia. These springs are hot, salty, rich in heavy metals, and they're acidic. Microorganisms thrive in these pools, even the pools of pH less than 1. That's more acidic than battery acid. Life adapted. Another example, the Atacama Desert in the rain shadow of the Andes Mountains. It is the driest land desert on Earth. This Martian-like landscape has been shaped by the wind and salty aerosols for millions of years. It has been one of the most challenging places to find evidence of life. And yet it's there, a few cells here and there. Life adapted. One last example, and this one really baffles me, Chernobyl. The diverse life in this agricultural region is punctuated by the presence of fungi that live off the radiation from the 1986 meltdown of Reactor 4. These fungi use the radiation, the gamma radiation, in the same way plants use sunlight to grow. Life adapted on Earth. Could life have arisen and adapted to the extreme conditions of other places in our solar system? We're going to find out. We will search for biomolecules, the organic compounds that make up life, its food and waste products. We may need to extend that search to other types of signatures to build confidence in that detection. We might search for active cells and catch extraterrestrial life in action. We might search for fossilized cells in ancient rocks and ice. Gavin explained that Earth is the only known biosphere. However, Mars is a close neighbor. Although it looks like a rusty, barren planet today, its history was very similar to Earth's in the beginning. Did life arise on Mars around the same time that life arose on Earth? Why are these two planets so vastly different today? Both Earth and Mars had a liquid core when they formed. Movement of this molten iron generated a magnetic field that shielded the atmosphere and surface from being blasted by ionizing radiation. Earth maintains its magnetic field, but not so for Mars. Convection of the Martian core slowed or stopped 4 billion years ago. Without the protection of the magnetic field, the powerful solar wind streaming continuously from the young sun crashed into the red planet, piling up in front of it like a bow wave of a ship. Except in this case, the wave is charged particles that electrically strip away the Martian atmosphere. This process continued for eons, regulated by the sun's activity, and slowly stripped away gases from the volcanoes and the rocks. With the magnetic field and atmosphere mostly gone, the rocky surface of Mars was bombarded by ionizing radiation from the galaxy and the sun. This radiation comes in the form of photons, such as UV, X-ray, and gamma rays, as well as charged particles. However, unlike what we experience here on Earth, all of these forms have an enormous amount of energy. When ionizing radiation encounters molecules, it changes them. Radiation damage to molecules means damage to life and the signatures that we seek. We know that life adapts. If life ever existed on Mars, did it adapt to the harsh radiation environment at or near its surface? Life has surprised us on Earth, and perhaps life will surprise us on Mars too. I have spent the last 4 years exploring Mars through the imagers and the instruments of the Curiosity rover. We have discovered that Mars is not really red. It's gray with a rusty skin. Mars is not really dry either. Liquid water on Mars formed rivers, deltas, lakes, maybe seas. It has been cold and warm, acidic and alkaline. Its surface and atmospheric chemistry evolved. It has organic matter and the key nutrients needed for life. We have only scratched the surface of Mars and begun to decipher its story. Did life ever live there? Is there life on Mars now? And could life live here in the future? Beyond Mars, we will search for life in the ocean worlds of the moons of Jupiter and Saturn. Jupiter has a magnetic field 20,000 times stronger than Earth's. The field produces a donut-shaped belt around the planet in which charged particles get trapped. Europa is a water ice-covered ocean world, and one of great interest as a possible abode for life. It sits right smack in the middle of Jupiter's magnetic belt, which means that it is being bombarded by intense amounts of radiation. Although the European surface is inhospitable, it may offer a glimpse of the chemistry of what lies beneath. Europa's thick crust is sufficient for protecting the underlying global ocean from radiation. And it is hypothesized that Europa may have hydrothermal vents stemming from its rocky interior, and if so, these are ideal sites for life, and they support the potential of life in the ocean. Now let's go to Saturn, where the moons are embedded in the rings, where we think life may exist on some of these moons. Like Europa, Enceladus is an icy ocean world, and in 2005, the Cassini spacecraft witnessed geysers of gas arising from the surface. These plumes are direct conduits to a deep ocean. We might search for signs of life by flying through these plumes. And then there's Titan, a rocky moon with seas of liquid methane and an atmosphere of organic smog. Titan is drenched in hydrocarbons, and it's cold enough to freeze most of them. Life as we know it is largely made of hydrocarbons. Although it may be a stretch of our imagination to think that life might live here, it is considered potentially habitable. Did life arise on Titan? There are possibilities for extraterrestrial life in our solar system. However, as Aki will explain, there are even more possibilities of life outside of it.
If we're going to look for life that's really Earth-like, we need to look for planets around other stars, exoplanets for short. When I started undergrad, we only knew of 9 planets in the solar system, actually 8 now. And in grad school, we thought exoplanets would be rare. 20 years ago, we discovered the first planet around another star. Since that time, we've gone from a few planets in the solar system to literally thousands of exoplanets orbiting other stars. And we have only searched a tiny portion of the galaxy with the Kepler space mission. We think there's at least one exoplanet for every star in the galaxy, which would mean over 100 billion planets in the Milky Way alone. So that's at least 14 planets for every human on Earth. And the Milky Way is only one of a myriad of galaxies in the universe. We've found that the planet formation process is more robust and easy than we thought, and exoplanets are common. They can form around all different kinds of stars, even ones not like the sun. There are even planets around binary stars like Tatooine in Star Wars. To our delighted surprise, exoplanets are not only common, but diverse. The first planets discovered are unlike anything we have in the solar system. They are hot Jupiters, massive gassy planets orbiting closer to their stars than Mercury orbits our sun. So in the solar system, we have two basic classes of planets. We have massive gas giants like Jupiter and small rocky planets like Earth. But there's all sizes of planets out there, from super Jupiters to Neptunes to rocky planets several times more massive than Earth, all the way down to true Earth-sized planets. So with all this richness of planetary real estate, it encourages us to start thinking more ambitiously, to search for those rocky planets that are actually like Earth. We may have already found some, but we actually can't tell right now what their surfaces are really like. So as Gavin mentioned, Earth's abundant surface life makes it unique in the solar system. And this is probably the only kind of life that we can detect from really far away. There might be other kinds of life on other kinds of worlds out there, but we probably won't be able to recognize it. So astronomers are really focused on finding the true Earth twins out there, and we will look for them in the habitable zones of nearby stars. So the habitable zone is the region around a star where an Earth-like planet is just the right temperature to have liquid water on its surface, the key ingredient for Earth life. So for the sun, the habitable zone stretches from just outside Venus's orbit to Mars. For bigger, brighter stars, the habitable zone moves out to cool off, like moving away from a campfire. And then for smaller, dimmer stars, the habitable zone moves in to keep the planet warm. Now this spectrum is how astronomers want to look for life on other worlds. It's the light from the Earth, as if it were really far away, separated by color. Don't panic, we'll go through it. Okay, so this rise in brightness on the far left is literally our blue sky. And this narrow dip comes from oxygen, which is produced by plants. These several deep dips come from water vapor. And then over here is a methane feature. So methane in our atmosphere largely comes from bacteria in the guts of our livestock and in swamps. So the Earth's atmosphere is full of biosignatures, gases that wouldn't be present in our atmosphere without life. Now, the technical challenge of ever seeing something like this is one of the hardest things scientists have ever thought of trying, and here is why. The Earth is 10 billion times fainter than the sun. So, if the Luxor skybeam, the brightest man-made light in the world, is the sun, the Earth is 4 candles on your dinner table. But astronomers actually observe things that faint all the time. The real problem is those 4 candles are sitting right next to the bright light. If we're looking at the solar system from 33 light years away, which is not that far, it's pretty nearby, the separation between the Earth and the sun is 0.1 arcseconds, or the width of a human hair from the distance of 2 football fields. So imagine trying to see those candles if they were right on top of the Luxor skybeam. We have to suppress the light from the star before we can see the faint blue dot next to it. There are a couple of different technologies people have come up with to do this. One of them is a star shade, a gigantic deployed screen that would fly tens of thousands of kilometers in front of a telescope. You'd be aligned with a star to block its bright light. But this telescope is a relatively small one. If we really want to get a spectrum like the Earth one I showed, we need a bigger telescope. So NASA has begun a concept study for a super-duper Hubble called LUVOIR, which will search for dozens of Earth-like planets and probe their atmospheres. In addition, it would enable a wide range of general astronomy, just like Hubble did. With powerful future missions, we could see the pale blue dot of Carl Sagan's imagining and have a fighting chance of finding life out there among the stars. So to put this grand endeavor into perspective, we turn to Piers.
The universe is really big and really old. Life has been on Earth for about 4 billion years. Now we know that in the universe, physics and chemistry are the same everywhere. A hydrogen atom here is just the same as a hydrogen atom on the other end of the universe. The laws of physics and chemistry work the same everywhere. Now we strongly suspect, based on an example of one, our Earth, that the laws of biology work the same everywhere too. And by that I mean the laws that Charles Darwin discovered for us. We think that based on these laws, that evolution can drive life to greater complexity and ultimately to intelligence. It's the smart thing to do. Now look at this tree of life. We can see intelligent animals that we're familiar with. Humans, elephants, dolphins. These creatures are very closely related to us. But look over here on the far right. There's one other intelligence, an invertebrate intelligence that evolved completely separately from the rest of us. They split off from us before brains were even thought of, when all creatures had were just a few nerve cells. Octopuses have an intelligence that's comparable to quite a lot of mammals, and it evolved completely separately. These guys are like little aliens living with us on our own planet. If you look at an octopus, you can see that its brains are actually distributed all over its body. Most of its brains are in its feet or in its legs, and they're connected to the nerve center in its head by a neural network. It's a distributed intelligence. But it turns out that they think pretty much the same way that mammals do. They solve problems, they seem to be self-aware, they have a short-term memory and a long-term memory, they learn, and they get mad. They basically tackle the business of living in a complex environment the same way that we mammals do. We think that we understand how an octopus thinks. So the secret of intelligence is in the software. It's not in the hardware. It's very likely that an alien intelligence would be comprehensible to us in the same way that an octopus's thoughts are more or less comprehensible to us too. We should be able to communicate with them if we met them. So you'd think there'd be plenty of opportunities for life to evolve somewhere else and maybe swing by the Earth, or at least call on the radio. But we haven't found any alien monoliths, or beer cans, or cigarette ends, and we have not heard them tweeting on the radio either. So, where are they? That's what Johnny von Neumann asked. Where are they? There are lots of theories about that, but I'm going to concentrate on the more plausible ones. First of all, there's the water trap. Maybe the worlds that have water on them are all ocean, for the most part. And if that's the case, you can't discover combustion, you can't make metals, so you can't make a radio or a spaceship. If our dolphin friends lived on an ocean planet, they would be stuck where they are, in the Stone Age, forever. We might discover intelligent life here, but they could be incredibly boring, talking endlessly about the flavors of different kinds of plankton and that sort of thing. Or maybe on a planet that has dry land but no metals, or very few metals. Same problem. You can't develop a technology. And how about the difficulty of interstellar travel? Maybe it's just too hard. It looks like a real challenge for us. It could be a couple of 100 years before we try that. Maybe it's just too hard. And then there's the great sci-fi standbys. Hostile races evolve, they wipe out everyone else. That's sort of an ugly end. I think we should move on quickly. This is meant to be a fun evening. And then there's another theory. which is that we could be the first. We could be the first intelligence to evolve in this part of the galaxy. Someone has to be. We could be the elder race. So here's a time history of Earth. When you look at all the time that life has been here, nearly 4 billion years, humans have only been around for a couple of 100,000 years, civilization for about 6,000 years, depending how you count it, and our technical era only for 200 years. When you look at this picture, it is obvious that the most likely first alien life forms that we discover will not be intelligent. They will be somewhere back here, equivalent to life on Earth during the first 3 billion years of evolution. Similarly, nearby life on an exoplanet is probably plodding its way up the evolutionary ladder. Remember how long it took us to get where we are, where we could even think about life elsewhere. So, what are the chances of us finding anything or anybody soon? Here's a timeline of missions for exploring the solar system with some notional ideas of what we'll be doing in the next 50 years. I think that over the next 30 to 50 years, we will have thoroughly explored every nook and cranny of the solar system and seen or determined whether there is life here or past life or not. I think there's a good chance we'll nail that one flat. And then there's a chance of looking for biosignatures in the atmospheres of exoplanets. Here's the missions. Again, pretty notional, sort of 30 to 50 year time frame in the future that we could see looking at exoplanets where we'd be looking for traces of life in their atmospheres. It turns out that we Earthlings have the prime real estate in our solar system as far as having a habitable environment is concerned. Most of the rest of the solar system looks like a really tough place to live. But you never know. We need to thoroughly check out our own backyard as well as the planets around other stars. We'd look like idiots if we failed to check for life close to home and failed for lack of trying. Now back to the beginning, John Holdren's question. Why do we even care about this stuff? We think it goes beyond just intellectual curiosity. It's in our nature because we humans grew up as part of nature and need to pay attention to it. I want you to imagine what humans could do in a couple of 100 years or so. Imagine a probe from Earth entering the solar system of another star after a journey of decades, maybe a century. Note the MSBR logo. What would it find? My advice to you is eat healthy, don't smoke, don't jaywalk, and you might find out. It'd be good to find out that we're not alone. Thank you for your attention.